Thanks a lot, Boaz, and thanks for the invitation. So this is my first time at Harvard, and it's great to be here, and it's an honor to speak at this conference. So this talk is called Around the Kadison-Singer Problem, which is a bit of a weird title, and what that means is I'm not actually going to tell you what the solution is. I'm just going to sort of tell you what some of the connections are, what some of the history is, and give you some examples to give you intuition for what the difficulties are and what the ideas are that get around those difficulties. So everything is joint work with Adam Marcus and Dan Spielman. So let me start by telling you what the Kadison-Singer problem is. So it's a problem that came out of mathematical physics and out of some work of Dirac in the 30s. And one question that Dirac asked is something like, well, how should you parameterize the states of a quantum system? So this is something that appeared in his book on quantum mechanics. And okay, what does this mean mathematically? Well, so for Dirac, a quantum system consists of observables and states. So an observable is it's a physical quantity that you want to measure, maybe like position, momentum, energy, or something like that. And mathematically, an observable is a self-adjoint operator on a complex separable Hilbert space. So you just want to think of that as maybe being L2 of the natural numbers. And a state is just a vector in this Hilbert space. And I guess he introduced this notation of Ket vectors. And so in this framework, the question is, well, what's a good basis in which to represent the states? And so the answer to this question depends on what you care about in your quantum system. And Dirac offered a prescription for doing this, which had 3 steps. So he said, first, well, find a family of observables that you care about that are compatible, which means that the operators commute. Okay? And what that means physically is you can measure them simultaneously, and there's no uncertainty principle, so you can they have well-defined values simultaneously. So find a maximal family of commuting observables, call this F. And then, since this is a maximal family of, since it's maximal, this has a unique eigenbasis, call this phi sub I. So you get some eigenvectors out of this. And then use this as your basis. So if you have some other state psi, just expand it in this eigenbasis, and that's your representation. So okay, so one crucial point in all of this, and the reason for choosing F in this way, is that if you make all the measurements in this maximal commuting family, this projects any state to a unique eigenstate phi sub I. Okay, and another way of saying that, the reason this is unique is that if each of these eigenstates is completely determined by making all of the measurements in this family F. Okay, so what this is saying is that this is some way of maybe conducting experiments that's sufficient to completely describe the state of the system. Okay. Okay, so this is called a complete set of commuting observables. This is some construction that people use in physics, and this is what Dirac said you should do. So so this seemed fine until von Neumann looked at this and raised some mathematical objections to this. Okay, so here are some of the objections. So the first one is you can't just diagonalize an infinite matrix, right? You could have an operator that doesn't have eigenvalues; it just has a continuous spectrum. So you may not be able to get these this basis of eigenvectors that you want. And the second thing is that, well, okay, Dirac got around this by introducing these objects called delta functions, but okay, delta functions are not actually vectors in a Hilbert space. So what are delta functions, right? So motivated by these problems, von Neumann introduced this sort of different mathematical framework of operator algebras for quantum mechanics. And the basic objects here are as follows. So the observables are still self-adjoint bounded operators. And okay, they generated this algebra of all bounded operators on the Hilbert space H, which I'm just going to call B of H. So the observables are not all that different. The notion of commuting observables is the same. So the operators have to commute, and this generates an abelian subalgebra A of B of H. But the thing that really changes in this framework is the notion of a state. And so for von Neumann, a state is just a positive linear functional on a subalgebra of B of H, which maps the identity to 1. Okay? So this is strictly more general. This includes as a special case the Ket vectors of Dirac. Okay? So given a unit vector you can define a functional row of A is just V inner product AV. And this, you can easily check this is a state according to this definition. So the vectors are still states, but this definition is strictly more general. Okay, so it contains all sorts of other weird objects that are obtained, for example, by taking limits with respect to non-principal ultrafilters and things like that. So this is a much more general definition. It contains some objects that are not all that tangible. Okay, what do I want to say about states? So the first thing is a convex combination of states is a state. That's easy to check. And so you can also check that the set of states is a compact set, so it's a convex hull of its extreme points. And a special role is going to be played by the extreme points of the set of states, which are called pure states. Okay, so a pure state is just a state that's not a convex combination of any two other states. Okay, so this is the setup. And Kadison and Singer were looking at this in the 50s, and they wanted to see if what Dirac said about, if there's some way to make sense of this, complete set of commuting observables in this operator algebra formulation. So what does that even mean? Okay, so first find a maximal set of commuting operators. That's just a maximal abelian subalgebra A of B of H. And then, okay, now you don't have these eigenvectors, and so the appropriate thing to consider is pure states on this abelian subalgebra. And, the question that comes up is, if you have a pure state on this subalgebra of commuting observables, is it completely determined by the values it takes on this subalgebra? Okay? And is it a complete description of the state of the system with respect to, let's say, operators that are not in the subalgebra? And what that means mathematically is, does each pure state on this abelian subalgebra have a unique extension to the entire P of H? Okay. And this is the question that they asked in this paper that was published in 1959. And they showed that the answer to this question is no. Okay. So they constructed some abelian subalgebras with the property that there are pure states on them that have two different extensions. And so this, this somehow suggests that this mathematical framework has some sort of problematic, indeterminacy about it. That you can make all the measurements in this maximal family, which is all you can hope to do anyway, but that somehow doesn't completely uniquely determine the state of the system. So they said, okay, no. But then there's one case, which is a very natural case that they couldn't settle, which is the case when A is the subalgebra of diagonal operators on this Hilbert space. Okay, so that's just the algebra of bounded diagonal matrices. And this is the Kadison-Singer problem. So if you have a pure state on this algebra of diagonal matrices, does it have a unique extension to all bounded matrices? Okay. So this was the question they asked in the paper, and they, the heart of this question is the uniqueness. So existence is really easy, actually. So if you have a pure state row on diagonal matrices, there's a canonical extension to all matrices just by, taking any matrix A and throwing away everything except the diagonal. Okay, so you can define this row not of A to be row of the diagonal part of A. That's clearly an extension. And so the content of the question is this extension unique? And in order to show that it's unique, you need to show that every extension agrees with this one, which by linearity amounts to showing that if you have a pure state row and you have an extension row hat, then it vanishes on every zero diagonal matrix. Okay. So this is the problem, and the difficulty is that these pure states are somehow very complicated. Right. So it's easy for vector states, but there are lots of other states, and that's why it's complicated. So what Kadison and Singer suggested is that they suggested an indirect way to access, to prove this conjecture without talking about the states. And the key observation is that whatever these pure states are, they behave in a really predictable way on diagonal projections. Okay. So this is our goal. You have row hat, which is an extension of some pure state row. You want to show it vanishes on every zero diagonal matrix M. So the observation is, which is very easy to prove, is that if you have a diagonal projection, which is just an infinite matrix with zeros and ones on the diagonal, then any pure state and its extension must be either 0 or 1 on this diagonal projection. Okay, this is like a two-line proof. And so the consequence of this observation is, well, if you have a finite family of diagonal projections that add up to the identity, which just means you have a finite partition, you have a partition of the integers into finitely many parts, let's say k parts, and you have a pure state extension rho hat, then it's equal to 1 on exactly one of these projections and 0 everywhere else. Okay, that's just by linearity. Okay, so it's easy to understand the behavior of these pure state extensions on these matrices. Okay, so this leads to this really nice concept of a paving. So this is a definition in the original paper. So an epsilon paving of a matrix M, so an infinite matrix M, is a finite set of diagonal projections P1 through Pk, which add up to the identity with the property that when you look at Pi M Pi, which is just the restriction of M to the submatrix corresponding to Pi, then the norm of that is at most epsilon times the norm of the original matrix. Okay, so the picture is something like this. You have some matrix, you have some M. Okay, it's infinite, but you're interested in partitioning into finitely many blocks, matrices like this. So each one is smaller than the original matrix in norm. Okay, and the main, the reason this is useful is that if a matrix has an epsilon paving, then for every pure state extension rho hat of M is at most epsilon times the norm of M. So the existence of a paving, of an epsilon paving, shows that this pure state has to be small on this matrix. And the proof is actually just a line. So what's rho hat of M? Well, by linearity, it's the sum of rho hat of Pi M Pj, because you can decompose the identity as the sum of the Pi's. And then on the previous slide, I said exactly one of these is non-zero, right? The other ones are 0. So by some Cauchy-Schwarz type argument, only one of these terms survives. So actually, if you have a paving, then rho hat of M is actually equal to rho hat of one of these blocks. And the paving has the property that these blocks are strictly smaller than the matrix, so you get that this is at most epsilon times the norm. Okay. So an immediate consequence of this is that if you want to solve this pure state extension problem, it's sufficient to prove something that you can call the infinite paving conjecture. It's sufficient to prove that for every epsilon, every zero diagonal matrix M in B of H can be epsilon paved. Because then you just let epsilon go to 0, and that's it. Okay? So the existence of pavings is an obstacle to non-uniqueness of these pure state extensions. And the gain here is that, okay, in the first part, you had all this talk about these, states and these weird objects. In the second statement, there are no states anymore. It's just a combinatorial statement about partitioning matrices into smaller matrices, infinite matrices. Okay, so that's what they did in their paper. And then the next, major step in this story was achieved by Anderson in 1979, who introduced a finite version of this conjecture. Okay, so here's his conjecture. There are some universal constants epsilon and k. Epsilon is strictly less than 1, with the property that for every zero diagonal finite n by n matrix, so just like honest to God, like thing you can write down on paper, there is a partition of the coordinates into k blocks, so that again, each submatrix indexed by these blocks has norm at most epsilon times the norm of the matrix. Okay. So these blocks, of course, correspond to the diagonal projections in the paving. So two things to note here. So one is it's absolutely crucial that the constants epsilon and k don't depend on n. Okay, this is a conjecture of matrices of all sizes. And also, it says here that you just need epsilon strictly less than 1, whereas in the previous conjecture, you needed to do it for arbitrarily small epsilon. Well, that's not really a difference, because if you can prove this, then you can take pavings of pavings of pavings of pavings and make epsilon as small as you want by iteration. Okay. So this is the conjecture. And what Anderson proved is by a limiting argument, this is equivalent to the infinite paving conjecture. So existence of infinite pavings is equivalent to existence of finite pavings for every n with these parameters that are independent of n. Okay, so this is now a very accessible problem. You can tell this problem to like a linear algebra undergrad. And once it got here, it was shown to be equivalent to a whole bunch of other finite dimensional linear algebra problems, which I won't tell you what all of them are, but here are some of them. And they're all conjectures about somehow partitioning a matrix into matrices of smaller norm, or partitioning vectors into subsets of somehow smaller in some sense. And there was some progress on these conjectures. So Bourgain and Zafiri showed that the paving conjecture is true with k equals log n, with a mild dependence on the dimension. So it's trivial to prove it for k equals n, right? You just take each entry, which is 0, but they proved that you can do it with k equals log n. This is not sufficient to get the infinite version because of the limit. And then Berman et al. Proved that you can do it for non-negative entries. And the result that we proved with Marcus and Spielman is that one conjecture in this family, pretty much the strongest one, which is called Weaver's KS2 conjecture, this is true. Okay? And this implies all of the other conjectures. So let me now tell you what this is. Okay, so this is a very simple combinatorial linear algebra problem about vectors. So suppose you have m vectors in Rn. Okay, so everything is very concrete from now on. I mean, the pure state stuff was maybe it was a bit abstract, but now, okay, you have m vectors in Rn, and we're going to be interested in their covariance matrix. Okay, so for any unit vector u, you can compute the second moment in the direction u, which is the sum of u inner product vi squareds. And that's just a quadratic form in the covariance matrix, which is the sum vi transpose. So I'm going to call that the covariance matrix. And okay, it's a quadratic form, so if you look at the level sets, it naturally gives you an ellipsoid. So here are some vectors, and if you plot the ellipsoid corresponding to these vectors, it looks like this. Okay. So I want to visualize these quadratic forms as being ellipsoids. And of course, the lengths of the principal axes of these ellipsoids are just the eigenvalues of the covariance matrix. Okay. Okay. So I'm going to be interested in what are called isotropic sets. So an isotropic set of vectors is just a set of vectors whose covariance matrix is the identity. So what that means is that the ellipsoid is just a sphere, and the moment is 1 in every direction. And the sort of almost just puzzle type problem that I'm interested in is I give you an isotropic set, okay? So, and I want you to partition it into two sets, red and blue. So I want you to color the vectors red and blue. And when you do that, you get two different covariance matrices. So you get two new ellipsoids. And I want this to have the property that these two ellipsoids that you get are non-degenerate. Okay? So they're close to being half times a sphere. So this original thing is a sphere. I want those things to be somehow half isotropic. So this is not so good. This doesn't look like it's very close to a sphere. This is also not very good. In fact, one of the sets here is degenerate. So it's really bad. But then I'm looking for a coloring that looks like that. Okay? So I want to partition into red and blue so that for each part, still the second moment in every direction is about half of what it was before. Okay? And then that's the problem. So what does this mean in terms of eigenvalues? Well, it just means I want the red eigenvalues and the blue eigenvalues to be bounded away from 0 and 1, let's say between 1/4 and 3/4. And since these sets are complements of each other, this is equivalent to just saying that I want both of them to be bounded above by some number that's away from 1. Okay? So balanced partition is a partition into red and blue, so the eigenvalues of both sides are, let's say, almost 3/4. Okay, so you can't always do this. Okay, so here's the canonical example of when you can't do this. You just take a standard basis. Okay, there's no way to partition into two bases at all. So certainly you can't partition into two half isotropic sets, right? So this doesn't work, but it's not just it's not just that you don't have enough vectors. Here's another example. You have these 4 vectors. 2 of them are really long and 2 of them are short. And the problem is that no matter how you partition it, because the long vectors essentially dominate this covariance matrix, no matter how you partition it, you're going to either get one huge ellipsoid and one tiny one, or you're going to get 2 really unbalanced ones. Okay. So the conceptual point I want to make is that if you have unbalanced, if you have vectors that are long, that this is an obstacle to doing this. Okay. If the norms of your vectors are close to 1, there's no way to partition into something that's close to half. And so Weaver's conjecture says that this is the only obstacle. Okay? So if you have an isotropic set and all the vectors have norms bounded by some sufficiently small constant, then a good partition always exists. And the statement of the conjecture is this: there are universal constants epsilon and delta, so that given an isotropic set where the squared norms are at most epsilon, squared norm is somehow more natural here, then there's a partition into red and blue so that the eigenvalues of each part are bounded by 1 minus delta. Okay, so you're just trying to beat 1. And any 0.0001 is fine. And what was known about this is you can prove this with delta equals 1 over n. If you're allowed to depend on n, you can prove this, and even this use some sort of non-trivial matroid theory to prove this. Okay, so the theorem that we prove is a strong version of this. So we say that, okay, if you have m vectors, the norms are bounded by epsilon. Then there's a partition into red and blue, so each part has eigenvalues bounded by half plus c squared epsilon. Okay, so not just bounded away from 1, but actually approaching a half as epsilon approaches 0. Okay, so that's the statement of the theorem. And are there any questions about the statement? Okay, you might wonder about this dependence on epsilon. You can also show that this dependence on epsilon is tight using some spectral graph theory examples. But anyway, so this is, yes?
It's the same as asking that there is a set in which the sum is at most below or half plus minus.
Yeah. So here I've just written in terms of upper bounds. Because B is the complement of R, this is the same thing as saying each set is at least half minus c squared epsilon half plus. Yeah. Any other? Okay, so let me show you some examples before getting to how the proof of this goes. So the first example, which I'm going to call classical for no reason other than all the matrices involved here commute, okay, is this. So suppose epsilon is some parameter that's going to be the norm of your vectors. And choose the vectors to be 1 over epsilon copies of each of the standard basis vectors scaled by 1 over squared epsilon, scaled by a squared epsilon, okay? So just copy each basis vector a bunch of times and shrink it to make the whole thing isotropic. So clearly you can check that the norms are all epsilon and this thing is isotropic. So here's a picture of this. So suppose I wanna partition this into red and blue. Well, what am I going to do? It's completely obvious. Let's just assume k is an even integer. I'm just going to, for each basis vector, I'm just going to make half of them red and half of them blue, right? So, because really this is not an n-dimensional problem, it's n one-dimensional problems, right? So for each direction, I'm just going to make half of them red and half of them blue. And then if you do this, then you can write down the covariance matrices are exactly equal to half the identity, and this is great. This is the best possible partition, right? So this is very easy. Okay, on the other hand, good partitions are exponentially rare in this example, okay? So if you were to try to do this using a random strategy, let's just randomly make each vector red or blue, then you would notice that this is very likely to fail. So I mean, there's a simple calculation. Let's make a random partition. Let's look at E1. What's the probability that all those vectors in that direction are red? It's 2 to the minus the number of vectors, so 2 to the minus k. But k is a constant, right? So there's a constant probability of saturating this direction, E1. And what happens in these directions is independent, so you can do a calculation and say, well, with exponentially high probability exponentially close to 1, one of these directions is going to be all red, okay? So actually, a random partition is horrible. Maybe not so surprising, but a random partition is terrible for this, unless the number of vectors in each direction is at least log n, which corresponds to the norms being at most 1 over log n. Okay? In that case, you get some concentration, and it works out. Okay? But of course, this is not good enough for us because we need everything to not depend on n. So this is the first example. The second example, which I'm going to call quantum, it really has nothing to do with quantum. It's just that it's everything does not commute, is the following. So let epsilon be some parameter. And choose the vectors v1 through vm to just be standard IID Gaussian vectors. Okay. And appropriately scaled. So according to an appropriately scaled covariance matrix, so the norms are an expectation epsilon. So maybe the vectors look like that. Okay. So does this satisfy the requirements of this problem? So you need to do a few calculations. So first, just by standard concentration inequalities, you get that, well, actually all the norms are very, very close to epsilon with very high probability. That's standard Gaussian concentration. And then, okay, we don't actually know that this thing is isotropic. So to do that, okay, you need to use a little bit of random matrix theory. So this, you observe that this covariance matrix is a Wishart matrix to sum of outer products of Gaussians. And then, okay, there's a theorem, the buy-in theorem, that tells you that with very high probability, the eigenvalues of this matrix are contained in the interval 1 plus or minus squared epsilon squared. Okay. So this is a random example, and with very high probability, this is very close to satisfying the constraints of this KS2 problem. And okay, since right now, let's say we're just interested in bounding by 3/4. Okay, then we're not that interested. These squared epsilons don't bother us. So let's just assume that let's forget about it. Okay, it's not a problem if we're just interested in some bound. We may as well assume these things are actually bounded by epsilon and are actually isotropic. If you want, you can make this happen by applying a linear transformation, but don't worry about it. Okay, so this is a valid instance of this problem, and now you want to partition this into red and blue. So what are you going to do? Well, so it's not obvious what to do if you actually had to come up with a rule, right? Because this is a truly n-dimensional problem. There's no way to say, there's no obvious greedy strategy for coloring this, because the eigenvalues are going to change in some sort of weird way because things don't commute, basically. So on the other hand, a random strategy is really great here, right? So if you just randomly color half blue and half red, then okay, the same type of calculation. So what are the red vectors? Well, they're also just, what's the red covariance matrix? It's a sum of outer products of Gaussians. It's also a Wishart matrix, just with half as many vectors. So by the same theorem, the eigenvalues are going to be between half plus or minus 1 plus square 2 epsilon squared, okay? So a random partition is great in this case, the same for blue, okay? So random instance, random partition, each part is itself a random instance, and so it's going to have very good eigenvalues, and so a random partition works great. So the situation here is it's the opposite. So good partitions are extremely common. They're with exponentially high probability, a random partition works, but it's very hard to specify a rule to find one in this example. And so this is sort of the difficulty with this question, that you have one type of instance where very structured instance where a greedy strategy works but random fails, and then you have another type of instance where random works but it's very hard to specify any deterministic strategy. And so then if you have a whole spectrum of things in between these instances, what if you combine a bunch of these things? How are you going to analyze that? Okay, that's sort of why that's somehow the core difficulty in this problem. We don't have methods that can uniformly handle this whole range of examples. So okay, so let me just say what you can do if you're willing. Let me just say what you can do fairly easily using known random matrix techniques, which is get this to work when the vectors have norm at most 1 over log n. So as I said, even in the first example, if their norm is at most 1 over log n, the random instance works. So let's just show that can be made to work in general. So what do? Okay, you choose a random partition. We want to show that the red eigenvalues are at most half plus some function of epsilon, and the blue ones are half plus some function of epsilon. So these are statements about two random matrices that are related to each other. So let's write this as a statement about one big random matrix. Okay, so 2n by 2n matrix, just embed these in blocks. So this is a block diagonal matrix. And of course, if the norm of this is bounded by half plus some f of epsilon, then each of these things is also bounded. Okay. And now the key thing to observe is that this is a special kind of random matrix. It has a very special structure. It's a sum of independent rank 1 random matrices. Okay? So for each vector vi, I'm going to define a new random vector called vi red. So red means random, which is just going to put vi in the top block with probability half and the bottom block with probability half. Okay? So it's a 2-point probability distribution. And I'm going to take these vi's to be independent. And then if you look at the sum of their outer products, well, that's exactly this matrix, right? So this random matrix is the sum of independent rank 1 random matrices. And the expectation of this matrix is half times the identity. So that's easy to check, right? That's the ideal balance that you're shooting for. And now the point is that there are some very well-developed tools for analyzing sums of independent bounded rank 1 random matrices. Okay, so this is a result of Rudelson, and the improvements to work of Trop, would say that if you have a bunch of independent random vectors whose expected covariance matrix is the identity, and which are bounded by epsilon, then the expected norm of this random matrix is at most 1 plus square root epsilon log n. So this 1 here is just the norm of the expected matrix. Okay, so that's the best you could hope for. This is saying that the expected norm is at most the norm of the expected matrix plus this square root epsilon log n. Okay, so this is a very generic result. It doesn't assume anything else about the structure of these vectors. And this is sort of like a Chernoff bound for scalar variables. The only difference is that it has this this dependence on the dimension. So these are in Rn, and there's a log n. And so if you plug this into your problem, you just get that, okay, you can solve this KS2 problem with this kind of error, which means if the vectors have length at most 1 over log n, it's fine. Okay. So given these tools, it's fairly easy to get this with logarithmic dependence on the dimension. And this, the problem is this isn't good enough because it depends on n. So our main theorem is this, which is somehow complements this matrix Chernoff bound. And what it says is if you have independent random vectors, expectation is identity, and the expected norms are at most epsilon, then the probability of the norm is at most 1 plus square root of epsilon squared. Okay? So again, this 1 corresponds to the norm of the expected matrix. So the deviation is about order square root epsilon. They're saying the probability of the norm is bigger than 1 plus square root epsilon squared is positive. Okay? So it's stronger and there's no dimension dependence, but it's weaker because there's no bound on the probability. And as such, we're really just using probability as a notation. There's really no bound on the probability. Okay. Okay. So and of course, if you plug the partitioning into this, you get the main theorem that I advertised, that you can partition all these, you can solve this KS2 problem. Okay. So let me say a bit about the proof. So let's think about how you might want to prove this. So what we're given is a bunch of random vectors with these conditions. The goal is to show that the norm of this matrix is small with some probability. So if you try some of the standard non-asymptotic random matrix theory approaches, the usual idea is you don't try to bound the norm directly. It's not such a nice quantity. So instead you use this variational characterization of the norm, or you control the norm using traces of high powers of the matrix, or maybe the moment generating function, and so on. And so you study these various functionals of this random matrix, and this is how you get bounds on the norm. And there are two drawbacks of this. So one is we know that we won't be able to prove anything with high probability, right? Because we know that it's simply false. So these methods typically are only capable of proving things that hold with high probability. And secondly, the Chernoff bound had a dimension dependence. There are a lot of random matrix results that don't have a dimension dependence. Okay, so maybe for some restricted class, you could imagine using those. And the thing I want to say about that is that most of the dimension-free concentration results for random matrices assume some sort of strong symmetry or regularity assumptions about the matrix, like that the entries are IID or comes from a log concave distribution or something like that. So it's unlikely to be able to handle the very clunky random vectors that we have that come from this partitioning. Okay, so the main idea is to use a different way to access a random matrix in a different way. So we're interested in A, and then the eigenvalues of A are the roots of the characteristic polynomial. So the idea is to look at the distribution of A by looking at the expected characteristic polynomial of A. Okay, so you literally just, for every A you get a polynomial, it has coefficients which are elementary symmetric functions of the eigenvalues, and you just average them. So you get this one polynomial of degree n. And okay, you can think of this as some sort of a generating function for averages of the elementary symmetric functions of the eigenvalues. That's the data that's contained in this polynomial. And this might seem a little weird because we're interested in the eigenvalues of this matrix, so we're interested in the roots. But what we're doing here is averaging the coefficients. And averaging the coefficients, it's not really clear what that has to do with averaging the roots or anything like that. Okay, so before I get to why this makes sense, let me just show you a couple of more examples. So here's one example. I'm going to call this balls and pins. So suppose k is an integer, let m be k times n, and take your random vectors to be v1 is just either equal to the first basis vector or 0 with probability a half. v2 is the same, v3 is the same, up to vk is the same. So for every basis vector, you make k independent random vectors that are equal to that vector, okay, scaled appropriately, or 0 with probability half uniformly. Okay, and you do this for every basis vector. So you can think of this as throwing m balls into n bins, where in each bin you have k trials, and you have probability half of succeeding in each trial. So if you do this, then okay, what covariance matrix do you get? Well, it's a diagonal matrix. The entries are just going to count the number of times that vector was chosen to be non-zero. Okay, so it's just a diagonal matrix, and each entry is just the number of balls, the fraction of balls that in bin I that actually were chosen or landed or whatever. Okay. So it's a very simple random matrix. The expectation of this matrix is identity over 2. Okay. However, as we discussed earlier, with high probability, the norm of this matrix is 1. Okay. So one of the bins is going to be saturated. Okay. So this is very far from the norm of the expected matrix. Okay. Okay. So let's calculate the expected characteristic polynomial. So these random variables are IID. So the expected characteristic polynomial is just the product of z minus xi's, where these are just the occupation of the ith bin. And since they're independent, it's just the product of the expectations. And since they're the same, it's just the expectation for the first bin raised to the n. And what's the expected fraction of balls that land in the first bin? It's just a half. Okay, so the expected characteristic polynomial is z minus half to the n. Okay. Now, that was some sort of a very easy calculation, but I want to make 2 observations about it that are sort of surprising. So one is that this is real rooted. Okay? So there's no reason to expect a priori that when you add a bunch of polynomials that have real roots, that you'll get something that has real roots. Okay? But in this case, it is. And the second thing is that the largest root of this expected polynomial is a half, even though almost all the polynomials that I averaged had a root that was equal to 1, right? I said with exponentially high probability, the largest eigenvalue is 1. So I averaged a bunch of things with root 1, but when I averaged them, somehow all of that stuff canceled out, and all I got left was this half. Okay? So all the bad events somehow cancel each other out in this example. Okay, so I don't know. Does this mean anything? Is it useful for anything? I don't know. Let's look at another example. So here you just have Gaussian random vectors. Let's take V1 through Vm to be IID Gaussians of the appropriate norm. And again, this sum of outer products is just a Wishart matrix. The expectation is the identity. Let's calculate the expected characteristic polynomial. So it's pretty easy because it's a Gaussian. You get that it's an associated Laguerre polynomial, which is an orthogonal polynomial that you may have heard of. Okay, so it's a nice polynomial. It has a nice formula, but I'm not going to write it. This polynomial is real rooted, and its roots are bounded by 1 plus square root n over m to the whole square. Okay, exactly what's predicted by the Bayesian theorem, which is also exactly what the norm of the typical polynomials in this collection is. Right? I said with high probability, the norm of such a matrix is exactly this number. So in this case, you're getting a very different kind of behavior. All the polynomials have largest root about this much, and when you average them, okay, the average also has largest root about that much. So these numbers are the same. So, this is sort of suggestive. I mean, is this numerology? I mean, in both these examples, the largest roots reflect the sort of desired behavior that you want for this partitioning problem, right? In the first case, it matches what the greedy algorithm does. In the second case, it matches what the random algorithm does. And so the question you might want to ask is do these numbers have any meaning? Is there any relationship between the eigenvalues of this random matrix and the roots of this polynomial? Okay. And so the punchline is that this is what always happens. Okay. So if you have a sum of independent rank 1 random matrices, if A is equal to some VI transpose, then the following 2 things always happen. So the expected characteristic polynomial is always real rooted. And the norm of the random matrix is less than the largest root of the expected polynomial with positive probability always. Okay? So in particular, this implies, for the previous 2 examples, the existence of good partitions for KS2. Okay? So somehow this object is capturing, in one case, this, rare events, these good partitions, by doing the right cancellations. And in some other case, this typical event. And the second thing is saying that, this is saying that you can somehow extract this information out of this polynomial, say something about the random matrix. So why should something like this be true? Okay, so as I said, it's not at all true in general. The expected characteristic polynomial of some other random, an arbitrary random matrix, typically is going to be not have real roots even. Okay. So why is this happening here? So to understand this, let's just ask the basic question. If you have two polynomials with real roots, when does the sum have real roots? Okay. Or when does the average have real roots? So I'm using this to refer to the average. So when does the average of two polynomials have real roots? And okay, when are they somehow related to the roots of the individual polynomials? So this is some sort of very elementary question. So not always. So here's a standard example of why not. If you add these two real-rooted polynomials, you get something with pure imaginary roots. So in general, nothing happens. But in the quadratic case, if you look at polynomials like this, whose roots alternate, then you can check that when you average them, the average is always going to have real roots, and the roots are actually going to lie between the roots of the individual polynomials. Okay. And this is sort of great, because this means you can then compare these purple roots to the red and blue roots, which is the thing we're interested in. Okay, so this alternating thing, this is a general phenomenon. So here's the sufficient condition in general. So the key idea is this concept of interlacing. So what's the definition of interlacing? So polynomials p and q with real roots interlace. So q interlaces p. If between every two roots of p, there's a root of q. So that's a very classical notion. And okay, this can be same for degree n. Between every two roots of p, there's a root of q. And then the main theorem, which is really the heart of this entire method, is this sort of thing which can be proved in one slide, which is if you have two monic polynomials, real-rooted, and they have a common interlacing, then the sum has real roots, and the largest root of one of them must be at most the largest root of the average. Okay. So here's the proof, just proof by picture. Here are my two polynomials. They're degree 3, red and blue. And they have a common interlacing. So there's a polynomial of degree 2 with roots, let's say, alpha 1 and alpha 2, such that between any two of these roots, there's an alpha I. And now, what does this common interlacing do? Well, I don't really care that much about the exact locations of the alpha i's. The point is it splits the real line into these three intervals. Okay? And inside each interval, each of my polynomials changes sign exactly once. That's what it means to be a common interlacing. So now let's look at the last interval, and let's maybe look at an interval whose endpoints are actually roots of these polynomials. And now let's observe that to the right of this interval, both polynomials are positive because they're monic, so they go to infinity. And then each of them change sign inside the interval. So at the left endpoint, they're both non-positive, right? Okay, but then that means that the average polynomial is also positive to the right and non-positive to the left. So the average has a 0 somewhere in this interval. Okay, and that's it. That means that the largest root of the average is greater than the lesser of the average roots. It's a continuity argument. And that's it. I mean, you do this for every interval, and that's the proof. Okay, as long as you can separate out the top roots from the second roots from the third roots and so on, you can add polynomials, and all these nice properties are preserved. And the roots of the average lie in the convex hull of the roots of the individual polynomials, which is the key property that we're going to use. So this seems very simple, but this is the main thing. Okay, so what does this have to do with our situation? Well, what it has to do is that our random matrices have a special structure, right? So our random matrices are sums of independent rank 1 random matrices. And what does this have to do with interlacing? Well, there's this Cauchy interlacing theorem, which is if you take a matrix, a symmetric matrix, and you add a rank 1 matrix to it, then the eigenvalues of the old matrix interlace the eigenvalues of the new matrix. So you can imagine the sum is generated by adding rank 1 matrices in some particular way, and each time you do that, you get two polynomials which interlace. Okay, so that's not a proof, but that suggests that somewhere that structure is present in these matrices as well. And that's what's used to, Adam will flesh out the details, that's what's used to prove these facts. Okay? The key thing is rank 1. Okay, and then in addition, so this is just true for sums of rank 1 random matrices. In addition, if you have this analytic information that the norms are small and the expectation is the identity, then it turns out you can prove a universal bound on the roots of all such polynomials. Okay? You can prove that the largest root is at most 1 plus square root epsilon squared. This matches exactly what happens in the Laguerre polynomial case. So in some sense, the worst example is that random example. You never have a worse largest root than that. And this is by some, I mean, this is analytic, this is, well, Adam will talk about this. But this also uses a rank 1 structure, crucially. So anyway, once you have these three statements, that just implies this theorem, right? So it says that the largest, this is at most the largest root of the expected polynomial positive probability, but that's just this number. And okay, and as I said, I mean, you can check that this dependence is tight and things like that. Okay, so that's it. I just want to summarize what I said. So I told you about this pure state extension problem from the Kadison-Singer paper, and then they reduced it to this infinite paving problem, which then by this limiting argument, Anderson reduced to a finite paving problem, which by some linear algebra maneuvers that I didn't mention can be reduced to this Weaver problem of partitioning vectors, which by this improvement of the matrix Chernoff bound can be solved in a dimension-free way. And the key idea in this is the study of this expected characteristic polynomial. And the reason this is at all a sensible object is that there's interlacing for rank 1 matrices. But I'm not going to say anything more, so you should go to Adam's talk. That's it. Any questions? Okay.
If you go into these three stages, these 3 steps of your
Yeah.
so which ones are the hardest? Or,
Well, okay, so this one took by far the longest. So, I mean, this one took like many, many years. So this is in some sense the hardest, I would say. Yeah. I mean, I would say the last step is the hardest by far. Yeah.
so let's give you again. It's interesting because you think once you have like just expectation of a
Yeah. So the reason it's the hardest is that